Welcome back, everybody. I hope you had a lovely lunch. By the time I got out there, a lot of the sandwiches had gone, but I hope you've had a wonderful, wonderful lunch. And welcome back to the room. As you know, there's a couple of parallel sessions going on. So there's this room and there's also the delegates' room downstairs. And this next session, Prospecting the Moon, Tools for Resource Discovery, is going to be chaired by Deniz Harries from ESRIC, who did the tour this morning. So he's going to chair all of the next speakers, and there are a lot of them, so I'm quite sure you'll be strict on time as well. And I hope you have a wonderful session. It's a delight to hand over to you, Deniz. And I'm not staying in the room because I have to do interviews outside with other people, but it is not because I think there's nothing very interesting here. It's going to be fascinating, and I'm very sorry I can't stay. But with that, please welcome Deniz, and he's going to lead the show for the next couple of hours.
Good afternoon, everyone. Thank you, Lisa. So, yeah, we just start right away. It's a packed session. We have 9 speakers in 2 hours. And Ben Bussey from Intuitive Machines will kick off this session with, I guess, a very interesting presentation on enabling commercial international lunar scientific exploration. The stage is yours.
Do I use this one?
You can use this one. Or there's one on the chair.
I didn't know if we could pick our own, like, walk-in music. Right, so I'm Ben Bussey, I'm Chief Scientist for Intuitive Machines. I want to give you an overview of capabilities that we have, focus on where I hope some of those might collide in what you are after, and then as an incentive not to ask questions, I have some videos and IM2 at the end, if there's time. Okay, so just the company in a glance. If you focus on the bit on the left, there are what we call 3 pillars to the company, and I'll go into a bit more detail. I think all 3 of those provide opportunities for this audience. So there's the delivery part, which is both surface, lunar surface, and orbital. There's the data transmission, and so comm relay and precision navigation and timing. And then there's infrastructure as a service. So that's putting assets on the lunar surface that are then used by multiple customers. So we had 4 lunar missions that have either occurred or are under contract. IM1 was last year, which was the first commercial company to put a lander on the surface and operate. IM2 was in March of this year. Like I said, I'll talk a little bit more about that at the end if I don't prattle on too long. IM3 is our 3rd mission. That is scheduled to go in Q1 of next year. We'll also carry the first of our comm relay satellites. And then IM4 will go later in 2027. So as you notice, they all look similar, and that's because all 4 use our Nova C class lander. So Nova C it's a C stands for Roman roughly 100 kilogram. It's actually about 130 kilogram global access capacity. It's about 4 meters tall, has a wide variety of mounting options. For your payloads. We have mechanisms that can drop either instruments or rovers off on the surface. The engine is a LOX methane cryogenic engine developed in-house. It's a high-thrust engine. It's worked well both times and gets you to the moon in 4 or 5 days. There's really 3 ways to get to the moon. You can do it in a few months, a few weeks, or a few days, and all 3 will tell you that their way is best. We also have designs for, when the customers require larger payloads, we have the Nova D variant of our lander system. It's derived from the Nova C, but it has improved capability and redundancy. A graphic of it is shown there. We have something called the Nova D Science, which launches on a Falcon 9, and that can deliver about 500 kilograms on the surface. Nova D Cargo can do anything up to 2,500 kilograms, depending on the variant of Falcon Heavy that you use. Important thing for stressing that is to really try and hammer home the fact that, yes, all these CLIPS deliveries that you're seeing early on are all taking roughly 100 kilogram manifests, but we have the capability to take more. So As I mentioned at the very beginning, IM is more than just a lunar lander company, but it has a coherent, broad strategy in what it's doing. So the Nova C is a technology leader, which leads to this multiple capabilities. And so we have the Micronova hopper. This is roughly 1 meter tall. It's a hydrazine monoprop system, and it can carry about 8 kilograms, 25 kilometers. If you take the legs and the landing system off the Nova C, you have the Nebula, which is a high-energy orbit transfer vehicle. You can think of this as almost like a proven third stage for a Falcon 9. It has enough delta V to do deep space missions like Venus, Mars, or asteroids. Zephyr is an Earth entry vehicle we're designing, which will do short duration experiments in Earth orbit and is fully reusable. The others I'm going to talk about in a bit more detail. We're one of the 3 companies down selected by NASA to provide the unpressurized rover for the Artemis crew. So lunar terrain vehicle, ours is called is Moonracer. We have an experienced team. We would actually launch this to the moon on a Nova D, so it fits on a Nova D class lander. What might be we use a trailer design for this, and that it can pull trailers that can carry about 800 kilograms of payload and have good power and comm. And so we've been looking at if selected, what we could do with those trailers, and and in addition to sort of thematic science trailers that we're looking at, we've also, to us, it's a really exciting platform for resources. You could imagine having a prospecting trailer as well as then an extraction trailer, because you can do a lot with 800 kilograms. You can have drills that go a lot deeper than 2 meters, or some fairly capable payloads from a power perspective. For smaller payloads, we don't do our own rovers. We collaborate with other companies. In Europe, we have an agreement with Space Application Services out of Belgium, who have their Love Me X rover. We're all interested in surviving the night. IM is looking at americium capability that can give you about 140 watts electric, and even though it says waste heat, as you all know, there is no such thing as waste heat on the moon. If you're trying to survive the night, it's good heat. And that's about we're designing this RPS system, and it's about a 40 kilogram system. You can survive the night, you can brute force it with batteries if you give up enough of your payload mass. This is potentially a more elegant, lighter weight system. So we are putting up infrastructure, we're putting up our own communication relays network. So that will be, when CLIPS first started, we made the decision not to rely on DSN for downlink. And so we have an agreement with a number of radio science dishes around the world that we use for our downlink when we do a mission. We're now expanding that to do com relay, and the first one of those will go up with IM3 next year, and the goal is essentially 5 spacecraft in elliptical orbits with Apolloon over the southern hemisphere, because it's focused right initially on supporting Artemis crew. But we also have the capability with the ground stations to do orbital determination. We demonstrated that with IM2. We used NASA DSN as a backup, but we were able to do orbit determination without using DSN. So IM3, I should have bought my readers. So IM3 goes early next year. As is always the case with Eclipse delivery, there's a NASA manifest shown up there, including a laser reflector from European Space Agency, and then the original PRISM, which is the NASA science instruments or suites that were selected, was out of Johns Hopkins Applied Physics Lab, and that's called Lunar Vertex. It's a lunar outpost rover with the APL instrumentation, and we're going to land at Rhina Gamma, which is one of the magnetic anomalies on the moon, and then Lunar Vertex will go explore it. Key to CLIPS is the fact that not all the payload is the original NASA manifest, and our 2 missions to date have all had significant component of commercial, and you'll see the same is true with IM3, and that can either be commercial as in payloads carried on the lander, or in the case of IM2, we actually had commercial payloads that were dropped off as rideshare. With our com relays, we're very excited to start to take the next generation of lunar data sets. We have about 40 kilograms spare capacity. We've decided we're going to put instruments on every one of these. It's also an opportunity, if you have an instrument that you want flown, that you can come to us and put it on one of these satellites. So on LDNS-1, the first com relay, we're flying a multispectral imager from Scanway in Poland. We have a thermal hyperspectral imager, a space radiation experiment, and some high-def video cameras. And then IM-4 will go later in 27. Its primary payload is the Prospect that we heard Dave Heather give an excellent talk yesterday, overview of Prospect, as well as a mixture of other NASA-provided and commercial payloads. And the goal is to fly LDNS 2 and 3, so 2 more com relays. So opportunities for this audience. So there's a rideshare opportunity. When we do a launch right now, we buy the whole Falcon 9. So we can just give you a TLI throw. That's what we did for 3 payloads in IM-2. Before we land, we go into lunar orbit, so we can drop off up to about 300 kilograms in a 100-kilometer orbit before landing. We're also looking at the potential of using some of that 40 kilograms spare capacity. You could do a drop-off also of a CubeSat from one of our com relays. There's hosted payloads on LDNS. We're also looking at the possibility of buying a 6 bus and putting that in a more dedicated mapping orbit. There's just acquiring new data. You may not want to fly an instrument, but you might have data that will help your business case or helps you move further forward. And so we can get you the data that you want, either with LGNS or a dedicated orbiter. Obviously, there's surface payloads. We're looking at survive the night capability, and then there's infrastructure such as com relay and LTV trailer. I've allowed myself 27 seconds, so you get a bit of video. This is IM-1 and IM-2 closing in the fairings. On the right, you can see 2 of the 3. These are both commercial ride shares. You don't need that, don't need that. So if you look carefully when I play this video, you'll see the little white dots, and I wouldn't say fly off, those were the 3 co-manifest payloads leaving. And then over time. Hey. So this is a movie it shows the equatorial region, and then I'll very quickly go. This is the poles. This is going over. That's Shackleton just coming into view, and then I will leave you with this one from the dirt. No, I won't. It has to stop. There we go. And then this is from 2 of the PAO cameras taken during final descent. You'll see a picture at the end. And I will stop there, so I might get one very quick question, maybe.
Yes. Thank you, Ben. We do have time for questions.
You can't see if you get any. It's great. I've numbed them. It's post-lunch coma. Well, I'll be here the rest of today and tomorrow if anyone either is shy or thinks there's something they want to ask later. Oh.
So Thomas Kurz, I'm from Philips Medical, but as a private person here, but I'm very deep in space for a long time. Question regarding the landing of the second and first, it turned to the ground. And
yes.
What are the? Did you consider the center of mass? And could you exclude and validate that this is not a problem for the next missions?
Yeah, very quickly. So very quickly, yeah. The center of gravity isn't an issue. If you think of it, it's 2/3 of your mass when you launch is fuel. So by the time you land, those fuel tanks are essentially empty. And so your engine is at the bottom. Your center of gravity is, in fact, incredibly low. The reason for tipping over both times was primarily problems with the laser altimeter. You can't land without altimetry information at the end, mainly because you end up with lateral velocity. It doesn't matter where your CFG is. If you land with meters per second of lateral velocity, you will tip. And so the problem both times was actually very different. The first time the lasers didn't fire. The second time they did fire, but what came back was too noisy to feed into the nav system. The important thing is to say we've done what we call a hot wash. We do know for IM2 exactly why it happened. And we've already said that for IM3, we're going to have dual redundant independent systems. So instead of one laser, we'll have 2 lasers and 2 of something else. So essentially, we'll have multiple ways of getting that outage information. But the reason for the tipping isn't the center of gravity. It's the fact we had lateral velocity both times. There's a reason in that graphic you show a lander coming straight down at the end, because that's what you need.
Thanks. So I suggest we move on to the next speaker. Thank you, Ben. And the next presentation will be given by Deniz Ölçek from the University of Oslo. And it's on active nuclear imaging system for investigating lunar water ice and geochemistry. So the stage is yours.
Thank you very much. I am an experimental physicist, also sometimes pretending to be a space systems engineer. And I'm more on the instrumental development side of things. And today I will be presenting to you about a fairly new study on a feasibility study that we started with our collaborators in Arizona and in Berkeley, California, using an active interrogation technique with potential applications in the exploration of lunar surface and beyond. So I'll start off with a very brief introduction of nuclear spectroscopy, which is a powerful tool for geochemical mapping on planets, moons, asteroids. So naturally, cosmic rays interact with the planetary surface, resulting in secondary neutrons and characteristic gamma rays. Also, we have natural radioactivity present that may be present in the regolith and the rocks. So by detecting these signals, we can study the chemistry of a planetary body. So from the local variations of neutron flux, as you can see on the top left figure, from the lunar prospector, it's a data set from Lunar Prospector's neutron detector. We can identify where the hydrated minerals may be. And the bottom right figure shows a comparison of gamma ray spectra from the Lunar Prospector and Kaguya missions, just showing how the elemental identification can be made using such data. So some notable missions that carried or will carry nuclear spectrometers. Most of them are orbital missions, and with the recent advances, we have an increasing rate of in situ missions. One thing to note here is the DAN instrument on the Curiosity rover. It's an active instrument as opposed to the other ones. The other ones are passive probes. So in the case of DAN, there is also a neutron source on board. So what do we mean by passive and active probing? In passive detection, the instrument measures the secondary albedo radiation as well as the natural radioactivity emitted from the surface material. And in the active probing techniques, we include a neutron generator on board, which enhances the sensitivity of our measurements, the measurement statistics. Also, the spatial resolution can be as good as 5 centimeters per pixel. And depending on how it's used, it can unlock some depth information. It's especially useful for planets with thick atmospheres like Venus, or in the case of Saturn's moon, Titan. So the active neutron technique that we explored during the study is also known as associated particle imaging. So in an API system, we have a 14 MeV fast neutron generator, which also emits alpha particles traveling in the opposite direction. And we detect these alpha particles on the other side of the generator with a position-sensitive detector, while we capture while we measure neutrons and gamma rays emitted from the sample, from the activation of the sample. So we correlate alphas and this detected radiation within nanoseconds and can create an image out of that. So since 14 MeV neutrons travel at about 5 centimeter per nanosecond in the air, and this can, of course, they are being slowed down inside the sample depending on the material density, composition, so we can achieve 5 to 10 centimeter per pixel spatial resolution. So this is how our setup looks like at the Berkeley lab. An API system typically involves a high-resolution gamma ray spectrometer, which is a lanthanum bromide scintillator in our case. And recently we added a neutron detector based on a click scintillator, which is sensitive to both gamma rays and neutrons, and which can become a part of the instrument that is currently under development, which is called Inspector. So we run some experiments with this setup, and the one I'm showing here is including some lunar subpole regolith simulant acquired from Space Resources Technologies. So we placed a layer of regolith simulant over a layer of high-density polyethylene, which is an excellent proxy for water ice due to its similar hydrogen content, and also carbon has some similar scatter cross-section properties to oxygen. I wish we had some of those fancy icy regolith simulants. So it could be interesting to use it in this type of experiment in the future as well. So in the top right image, we have the spectra from both layers. So this figure demonstrates the superpower of the API system, basically. In red, we see the regolith simulant spectrum with silicon and oxygen peaks that are abundant in this regolith simulant. And we have a clear carbon peak from the polyethylene layer, which is absent in the regolith layer. So from the arrival time of the detected particles, we can reconstruct spectra from different depths. And one thing to point out is we don't observe a gamma ray peak associated with hydrogen here, because those are due to neutron capture events, which are delayed signals that fall outside of our API coincidence window, which led us to include a neutron detector to measure hydrogen and potentially image it. So we used an inorganic scintillator called CLIC, which is sensitive to both neutrons and gamma rays, and it offers a capability of radiation discrimination based on pulse rate. We didn't just select CLIC for this capability, but also it has flight heritage with the Luna Map mission, and it will be on board one of Firefly's upcoming missions called Lunar Rise. So from the variations in the neutron spectrum, especially typically in the variations in the thermal neutron peak, which CLIC is able to capture effectively, we can study hydration levels. But in this study, we are particularly looking at imaging capability of CLIC with fast neutrons. So to test that, we used various samples with different compositions. In the picture, I'm showing an experiment we've done with 2 cylinders, one made of steel and the other one made of high-density polyethylene. One is a H-deprived material that is rich in iron. The other one is an hydrogen-rich material. So we were able to measure a variety of, we were able to measure neutrons with a variety of energies with click and isolated fast neutrons to create the images you see in the top figure, which is a fairly good image, but with measurement time, we are hoping to improve the clarity of this image and potentially use a neutron detector, perhaps that is more sensitive to fast neutrons. And in the bottom figure, I'm showing the gamma ray-based image, which is missing the hydrogen signal. So the fast neutron image is especially valuable because it includes the hydrogen signal. One caveat here is that polyethylene includes both hydrogen and carbon. So in order to discern the contribution from these two nuclei, we also use gamma ray spectrum and simulations. So stay tuned for our upcoming paper that will be about this effort. So future institute missions can be benefiting from a dual API imaging system, and our future efforts will include making such an instrument more compact and space appropriate. Thank you.
Thank you. Other questions? We have some time. I've got a quick one. So other elements like lanthanides which have a high neutron capture cross-section, would you be able to detect them at really low concentrations, potentially?
I can't really say. Yes, we would need to run experiments with varying compositions. Yes. But for example, this simulant contained trace levels of calcium, magnesium, and we were not able to see them, for example.
Yeah. The reason is there are the creep regions on the moon, which are potentially enriched in phosphate minerals that contain the lanthanides. Mm-hmm. So that would be super interesting if that would also become a use case for this. Okay. Any other questions?
I think there is one over there.
Yes, Suleiman.
Yep. Thank you. That was very interesting. I just wanted to add that we have a passive neutron spectrometer, which was on IM2 mission, and we got a short time operating on the moon. So this is really a good technology. It's a passive one. It's a small one. It's a polylunar water snooper. I just wanted to add to the neutron spectroscopy.
Okay. It was an active technology?
It's a passive.
It's a passive technology.
Yeah. It's just a passive. A small one. It's a half a CubeSat. Or less than half a CubeSat. It's a very small instrument, and we got some data during transit. And you know, Ben Bussey just mentioned IM2, so we had a short time operational time on the lunar surface, out of normal temperature range because we were in shadow, but minus 60, minus 55, we have been operating nominally. So it's not enough to get good data, but we have been there. So just in addition, this neutron spectroscopy is really a good stuff, and active could be even much better. Yeah. Thank you.
Thank you for your comment.
Thank you. So I suggest we move on to the next speaker. Thanks a lot again.
Thank you.
And the next presentation will be from Igor Drozdovskiy from the European Astronaut Center, and it will be on real-time identification of minerals from multimodal spectroscopy for in-situ surface exploration.
Hello, good afternoon. I'm an expert scientist working, as been just announced, at European Astronaut Center, but expert is also one of a team where I'm part-time involved in development, supporting development of different types of analytical instrumentation for future moon exploration or future space flight. So CAPES and Pangaea team itself, it's a collaborative endeavor, and our team consists actually on the multidisciplinary team consists of, first of all, scientists like me. I came from astrophysics originally, but I actually involved for the last 8 years in geophysics and specifically mineralogy. And we also have engineers, both for hardware and software, and there are some of them at ESA and some of them external collaborators. And I would present one of the projects developed for the hardware development. Also, we have instructors, the people who work with astronauts and know in depth how difficult it is to develop any kind of analytical instruments which needs to be used by highly trained, very skilled astronauts, but nonetheless not necessarily professionals in mineralogy or geology. And finally, we have also within the team the people who constantly actually involved in operations, space operations, so it's not for nothing what real time is actually one of a part of this title, because what is critical for human space operation, and it would be also critical for human exploration of the moon, is a time. The surface area will be time limited. The attention needs to be spent between different things, and the list of the things we want to do, then the analysis of different types of minerals would be time consuming. And another important thing is that we're not only relying on one source of information. We also want to share this information, first of all, with explorers on the field. And this information needs to be a specific format that you can quickly digest and highlight of importance of the resources you discovered. But also you need to share this information in real time as soon as possible with any support rooms. It can be science support rooms, but it also needs to be available to the ground support operation rooms in order to see if something is not working well. So it has to be shared between different people. Real time is critical. What else is critical? So the goal of this project is to develop a set of software and hardware tools for the real-time in situ recognition of geological materials. So we believe that real-time high-confidence mineralogical analysis will be of critical importance for future human and robotic explorations on the moon, but maybe other planets, both for science and resource prospecting. That's why I'm here. Moreover, we actually see this tool set could have a potential for terrestrial applications. For instance, we already use a part of this tool set in our astronaut training, where we have this tool set already embedded in our mobile computing devices and portable commercial off-the-shelf spectrometers, that is using in order to assist the astronauts, our trainees, in their observational skills. We also used this tool set in order for ourselves to develop operational constraints, strategies, and analytical methods for planetary explorations. So what we have learned in essentially from a few years of usage of different types of analytical tools and different types of software and reference information during the Pangea training campaign, but also we have been involved in technological test campaigns, both ESA and ESA ESRIC challenge. Prospecting challenge was one of my own experience, which I'm very was happy to participate, is that usage of a single spectroscopic methods for recognition of mineral resources specifically has its own limitations. What is clear for us that with one single spectroscopic method will be not enough in order to cover a wide range of possible samples that we want to actually recognize, identify. Another thing is clear that in order to do this work really efficient and to be more or less well integrated, the development of hardware instrumentation, calibration data, which is actually second thing on here, we called mineralogical database, and the software which is used for recognition of different kinds of spectroscopic features versus the resource needs to be developed together, integrated together, and tested together. And the earlier we will start this process, the better we will get the final results, because the main delays usually happens when the different projects are being integrated in the last moment and the things are not really compatible, or we have some kind of delays. So An important part of this integrated tool set is actually instrumentation, and I started with a project that actually been initiated about 8 years ago. And then it, of course, takes a lot of time in order to identify goal requirements and convince ESA to support this project in financing. An expert team at a certain point decided to initiate the call of the proposals, and an industrial consortium, or let's say consortium which won it, is shown on the right hand of the slide. It's led by Instituto Nacional Técnico Aeroespacial in Madrid, and these are the team members, actually principal investigators, which are already been involved in different, let's say, development of different spectrometers for space applications, specifically robotics like ExoMars, Mars 2020, and other missions. And they ask them to actually develop spectrometer for usage by astronauts. So this is something that seems to be easy, because it's actually would be for not for the space at this moment. We are currently targeted the only TRL4 level for this project, but we ask them to develop, first of all, combined instrument. Second, this instrument is supposed to be co-aligned measurement spot. And the third important part, which we ask them actually, that this instrument needs to be wirelessly communicating using standard space protocols and data exchange formats in order to exchange the information in real time with, let's say, science support and the ground operations. So last year, we were poster where we had the first initial, let's say, mock-ups of the instrument. The instrument have been actually finished, developed, and delivered to European Astronaut Center. And now we are starting with validation and testing campaign. And again, we main actually first initial, I would say, rehearsal of this kind of test is on the background of this photo. For the testing, we are planning to use the new artificial analog environment that's been built near the European Astronaut Center as a collaboration between the German Space Agency, DLR, and ESA. It has a name, Luna. And that venue of, let's say, that environment fits very well because we can actually simulate not only environmental conditions, meaning the lighting, different lighting conditions. We also have very good high fidelity samples that actually being both for regolith and the boulders. And particularly for the boulders, these are very much relevant to the moon, both for the Mars and high Alliance areas. We also have impact eyes, so we can actually test how well any kind of analytical instrumentation can identify any of these resources, either being in, let's say, in the powdered form, or the granular form, or they're being actually part of a rock or other kind of a mineral compound. And finally, what I didn't mention, that the consortium developed actually two different instruments that allows to combine, first of all, Raman spectroscopy. And Raman is one of the techniques I think is very well known, and specifically for the moon has a lot of benefits of using. One of them would be is that it's very good for identification different types of silicate minerals, and at the same time, it's also one of the technique that actually allows to have a spot size. Let's say this instrument will have 100 micron size, so we will have very high, let's say, resolution of results. At the same time, we also want to have a good understanding of impurities, let's say, of different elemental abundances. Therefore, as a second method, in one instrument would be XRF, X-ray fluorescence spectrometer, and second instrument would have combination of Raman and the LIBS, laser-induced breakdown spectroscopy, where requirements in our, let's say, original statement of work was that we wanted to have this instrument as high quality as possible, so don't expect this instrument to be compact. But it's, again, we started only the first initial campaign, and this is only the initial phase where we would Based on this campaign, we would select which of these two instruments would be selected for the following up phase and to prepare it for the next phase, space-ready instrumentation, and which elements needs to be redesigned. So considering the time, I would skip the part that more or less our own contribution to this project, which involves, and I would just go immediately to the summary, because it's actually tell everything all together. So in order to actually test the instrument itself is just the eyes. For this eyes, you need actually good reference data. We have spent some time in order to collect reference libraries, and these are covering both molecular and atomic spectroscopic methods, but the real world samples with spectra, which most of the spectra we have is for molecular spectroscopy, of course, and for XRF and LEAPS, we simulated a lot of spectra based on the known Monte Carlo simulation and in known, let's say, atomic transitions. Again, these spectroscopic libraries will be as a training data set for our machine learning software, and software is customized specifically for field operation, meaning that the machine learning models will be very compact in terms that we need to be run on relatively mobile computing devices rather than on, let's say, computing cloud. And it can be even embedded in the future space instruments. We also clearly understand that the real minerals are not a pure end members. We will have a composition, so we have worked a lot. And the third thing for exploration, supervised classification will never discover new minerals, therefore we actually following in our machine learning development step, incremental learning, where we actually can add a new, not yet known minerals. Moreover, each of the model would improve with the new additional data. So this is more or less our current situation. We have an instrument to test. We have a relatively sophisticated software. We also already conducted the first test of all system in terms of how fast and accurate it perform, but more results would come very soon. Thank you for your attention, and if you have any questions, please contact me. This is a QR code or email, or just ask questions here.
Thank you, Igor. Other questions? Does not seem so. Then I would suggest, for the sake of time, we move on to the next speaker. Thank you again, Igor.
Thank you.
So next up will be Francesca Esposito from the Italian Institute for Astrophysics, talking on exploring lunar resources using advanced techniques and machine learning, focusing on rare earth elements. Rare earth.
Okay, good afternoon to everybody. I am a researcher from the Italian Institute for Astrophysics, and today I would like to give you some short hints about a very interesting and ambitious project that we are developing together with our colleagues of the National Research Council in Italy, so the two of the major research institutes in Italy. This is in the context of a very larger program that is named PRORIS and is funded by our Ministry of Research. This project in particular, which I will talk today, has been funded with 5 million euros by the ministry. The idea is to be able to have in the future a capability of search for and mapping lunar resources. And in particular, we will focus in our project on two of these resources. The first one is water, and the second one are earth rare elements and rare metals, such as of the group of platinum. What about water? You know that water has there are several evidence that water is present on the moon since 2009, when the NASA spectrometer M3 that flown on the Chandrayaan Indian mission detected the spectral features of water in the near infrared. So here you can see a map of what they detected with a concentration generally focused in the poles, and in particular in the South Pole. The problem is that we don't know exactly which is the origin of this water, and in general in the internal solar system, which is the distribution on the surface of the moon, the abundance, the capability that we can have for extract this water, and the form in which we can find this water, if in form of small pebbles or ice, or embedded in the regolith, or in some water-bearing materials, and so on. So what is needed now is to have some detection techniques, some instrumentation that will be able to respond to all this question by measuring on the site, so at the level of the surface. This will be the topic of CNR colleagues that unfortunately weren't able to come today. In their presentation, they will show the instruments that they were developing inside this PRORIS program about the detection of water. I will focus instead on the detection of rare earth elements. That is the focus of INAF in particular in this project. You know that REE are not so rare on the Earth, in the sense that they are widespread on the surface of the Earth, but there are few regions where there is a higher concentration that can justify the extraction. So few regions in the world where we extract these materials that create also some geopolitical issues. On the moon, instead, there are some evidences that there are a larger region where there is a big concentration of rare earth elements, and this is in the Oceanus Procellarum. We have some evidence from the map of thorium that was given by the NASA Prospector mission, but also Kaguya mission. Thorium is a good indicator of the presence of rare earth elements, because when the rare elements are there, also thorium is there, so it is a good indicator. And another indication is the sample that have come back from the Apollo missions. As you can see in this picture, this A14, 12, 15, these are the landing site of the Apollo mission. And in particular, 3 of these Apollo 12, 14, and 15 brought back some samples that showed the presence of high concentration of rare earth elements. Okay, but in any case, excluding the laboratory test of samples, it is very hard to find and to detect the rare earth elements on the surface, because they are embedded in very small percentage in the structure of phosphate crystals that have the size of 50 microns, more or less. And an abundance, for example, in these Apollo samples, around thousands of micrograms per grams. So it is impossible to find them, to detect them from the orbit. And it is also difficult to find them on the surface. A technique that is generally used on the Earth is X-ray spectroscopy, so the detection of X-ray fluorescence. But this is a very precise instrumentation that can scan the material at a space resolution of 100 microns or some millimeters. So you can imagine that you cannot scan all the surface of the moon at this kind of resolution. So you need to find a technique, a strategy to find the better place where to make this scanning. So we, in this project, are planning to develop 3 instruments that will work in synergy, in a sequence, in order to reach the interesting sample to be analyzed. The instruments have all high heritage in INAF because some of them have already flown or are flying just now in other space missions in other contexts, and we are adapting them to the lunar environment. So technology is quite mature, and the project will last 3 years, and in this 3 years we hope to be able to produce at least some of the demonstrators of some of these instruments. So one is, of course, a gamma-ray spectrometer and X-ray fluorescence spectrometer that are two instruments in just one compact instrument. The other one, we have other two instruments that are vis camera, so camera indivisible. The first one will study the fluorescence from material that is stimulated by an ultraviolet source. And the second one is a stereo hyperspectral camera that will study the reflectance spectra from the material. So how we imagine all these instruments will work together? So we imagine they will accommodate on a small rover. The first measurement will be done by the gamma-ray spectrometer. We ask to the rover to have a round of 360-degree scanning all the surface, checking, finding for the peak of thorium. This kind of measurements has a very poor space resolution, spatial resolution of the order of 100 meters. So you can just say to the rover, it seems that there is a peak of thorium in the northeast direction, so please go there. So the rover starts driving in that direction, and then two other instruments, the two cameras that are synergic and complementary. Why they are complementary? Because when you find very low concentration of rare earth elements, the reflectance spectrometer is not sensitive to this small quantity, so it is blind, while the fluorescence camera has more sensitive diagnostic feature, so can detect these minerals. Instead, if there are high concentration, there is no more fluorescence, but the reflectance spectrometer can see the features. So these two, in parallel, will examine the samples, the regolith, so to reduce the detection surface from 100 meters of the gamma detection to meters and then centimeters. When we reach centimeter scale, so we are just looking at a sample or a portion of regolith, we can start the very precise measurement with the X-ray scanning that is able to give abundance, a kind of rare earth materials that are embedded in the sample. I would just close my talk with this slide. That is a paper from an Italian economist that is a professor of, he has just passed some years ago, a professor of the Bocconi University in Milan, that developed a very interesting economics model for moon mining. In this paper, he analyzed if the moon mining is truly cost-effective for a company. The outcome of this is that no, it's not cost-effective, but if this is just if the company works alone and efforts alone on its own, all the risks related to the prospecting and exploration phase. In case in which this phase is shared with the public research community, then this could be cost effectively. So if there is a partnership, a public-private partnership, in order to reach this common goal, this could be very interesting for all of us. So the idea, the message behind this article is that Please consider that also the scientific community is a stakeholder in this field, and we are happy to participate in a private-public partnership in order to reach this common goal that we share all together here. Thank you so much.
Thank you. Other questions? Yes, multiple. Lucas?
Thank you. Jakub Ciążela, Mirrors Mining Data Services. My question is about the phase that hosts rare earth elements. Is this mostly apatite, or there are also other phases that you've identified in the Apollo samples?
Sorry?
I mean, what mineral hosts rare earth elements?
Phosphates.
Yes. Is this apatite or also other phases that you identified?
Apatite, but also other phases, just xenotime.
Right.
And there
monazite?
is monazite. Yes, several. So more or less the same that we find on the Earth.
That makes sense. Thank you very much.
Thank you.
And one question in the front.
My question is then the overall range which this, let's say, rover instrument can detect furthest rare earth element, then, as you mentioned, a couple of hundred of meters, so like 200 meters, 300 meters. What would you expect?
No, we start from far, okay? But with the X-ray, we need to be closer and closer, so at centimeters.
Yeah, but when you would start the exploration, what would be the furthest distance you would first already detect that that's an area which makes sense to go there and make a more precise analysis?
We start at meters scale.
Okay,
yeah.
Thank you.
Okay, thank you a lot. I suggest we move on, and the next speaker unfortunately cannot be here. So instead, we switch briefly to lunar infrastructure, and we have Douglas Morrison here, and he has now the challenge to explain how we bridge between the rare earth prospection and the lunar infrastructure, but I'm sure he can. You're welcome.
Good afternoon. I'm very thankful to the organisers to shift me from my presentation tomorrow to this afternoon because I have to be gone tomorrow, unfortunately. So this is where we are. Lunar Surface Development Engineering, the Earth mining. So if we're talking about mining on the moon, talk about mining on the Earth. We have to produce between 2 times and 5 times more metals to make the energy transition successful before 2050. If we don't do that by 2050, climate change becomes basically uncontrollable on the Earth, and very bad things start to happen for very large numbers of people. So this is why we're trying to do what we're trying to do. That's what mining looks like on the Earth. These are massive open pits that are producing something between 100,000 and 200,000 tons per day, every day, 365 days a year. That's how big they are. You can see the small half-ton truck here, and that's the scale of the major haul trucks that we have, and bad things sometimes happen. And that's not, it should be never happening, but it's not, it happens way too often. And no, that truck was not empty of people. This is what it looks like underground. It doesn't look that much different. It is much smaller, but in actual fact, in this environment, we have to control the roof, because now you're going to have rocks falling on your head if you don't do that other pieces of work well. So it's still big and brutal, but on a smaller scale than it is in the large open pits. But even with this size of equipment that we have here, we still have this individual on the left-hand side still doing this material with a handheld drill in some mines in the world. And the workhorse machine that we use in the underground mines is this LHD. It's now 35 years old. It hasn't changed significantly in the last 35 years. So this industry is one that is using a technology platform 35 to 40 years old. No other sector in the economy is using a 40-year-old technology platform, except mining. So this is where we are. When I started mining in 1980, we were still using these machines in black and white, and I like to use with my students the black and white photographs because they think this is old-time mining. No, it's only just 40 years ago. And the other thing that shocked me when I did this was to realize that we were using this kind of equipment, the one in the middle with 1940 to 85. I actually ran this machine in 1980 myself, and that was only 8 years after Apollo stopped in 1972. So that's the gulf that we have to bridge between what you're trying to do in space and what we are actually physically doing in mining today. These machines are actually very inefficient. The one on the right-hand side, 80% of the fuel, 80% of the energy used by the machine on the right is used to move the machine, and 20% of the energy is used to move the product. On the old machine here, it's actually the other way around. It's a much better balance in energy. So although the scale is wrong, we want to be moving a lot of material, we need to be moving it with much, much more energy efficiency than we do. So that's why the machine on the right will never be used. That kind of effectiveness here cannot go to the moon. Don't even think about taking it to the moon. If we do anything on the moon for production, it will be this kind of scale and this kind of efficiency. Has to be. Now, to take a step away from the worst conditions we have on Earth are Antarctica. And this is what we were doing 100 years ago with basically what we might call Antarctic adventures. And we were going and living in a wooden hut with very, very rudimentary conditions. And the definition, my definition of adventurous activity is there is no backup plan. If things go wrong as you are walking to the South Pole, dragging your own sleds of supplies, you're going to die. And they did. These ones did. Amundsen came back, but he was using dog teams, and he had the advantage of being able to eat some of the dogs on the way back so that he was to survive the trip. This is what we have in Antarctica today, that massive infrastructure, planned infrastructure called McMurdo Station in the Antarctica, and it supports basically not much bigger than a single apartment building on the South Pole. The Amundsen Scott base is supported by the McMurdo Station, a massive infrastructure that you have to support a very small number of people at the South Pole on Earth. So what do we have on the moon? If we're going to start setting up infrastructure and doing sophisticated things on the moon, if we're going to use people, then you have to have the same kind of scale, at least that, because the size of your backup system has to be proportional to the distance that you've gone and the severity of the conditions. There are no conditions on Earth that are as severe as the surface of the moon, in terms of temperature changes, in terms of the aggressiveness of the regolith, etc. So here's where we are. These are still, actually, I would call them lunar adventures, because as we see with these vehicles that have landed on the moon, most of them unsuccessfully landing on the moon. So here we are in the 21st century, in 2025, and most of the recent landers that tried to land on the moon were unsuccessful. And that is an adventure because there is no backup plan for this. If it goes wrong, you crash on the moon, too bad, move on to the next example. That is not a professional exploration exercise. No mining operation, no matter how remote on Earth, leaves people stranded in that location if things go wrong. You have to have a backup plan from plan A, you have a backup plan for the backup plan, and a backup plan for the backup plan of the backup plan. There has to be a way to make sure that everybody is recovered safely and well. At least you have to have several levels of backup plan. And adventurous systems, as we are using now, cannot move us into the future. That is not a professional, modern 21st century enterprise. So, what can we use? I was very happy to hear about the other landers that have landed recently, but here we are. That's just the Apollo lander, dedicated, very successful. Between 69 and 72, they had 6 successful landings and takeoffs. And right now, apparently in the 21st century, we can't replicate that. Just to say, so you can use these as dedicated landers, just not to return, just to deliver infrastructure material in order to set up the absolutely necessary infrastructure you need for human beings. If we plan to send people there, we have to be prepared for that. So one of our difficulties is with these pictures on the right-hand side, which are fantasy pictures, we're all contaminated by the idea of Star Trek, etc. I've had to tell students at the university not to write in their essays, when are we going to develop trilithium crystals? There are no trilithium crystals. There are not going to be trilithium crystals or transporter systems. So we have to move away from that and come back to the realities of what has to be done to make this happen on the Earth, and we could do that. So there's a list of things you can do. If you're going to build infrastructure, it has to be autonomous. We can't be sending astronauts to oversee the construction of infrastructure on the lunar surface. Rover vehicles will be for construction of that infrastructure, not for roving. There is no Sunday drive for picnics on the moon. We're not just roving for the sake of roving. There are other ways to move things and people around. The activities we need to have are to clear the negative, capture it, sort it, package it, store it and deploy it as protective barriers, groom the bedrock surface if we have to, capture and store the debris from that process. Then you can begin to build a human habitat from lander material that's landed here, implement the replacement manufacturing that you have to have, because the lunar regolith is far, far more aggressive and wear-inducing than anything on planet Earth. So we have to be replicating the machines we have with materials that we found on the lunar surface. We can't keep sending repair material trip by trip by trip. So here we are. If you look at this, is just the Apollo system. You can see how this volume, the lower volume, was actually roughly 4 meters wide, 4.3 meters long, and 2.8 meters high. That's the container. You can actually see, instead of having the return module on the top, you could have 2 other sections which can be used as linking to the larger room volumes that we have. So this can be packed with material, empty the material, then use those containers, just as we sometimes talk about container ships, and use those container boxes for homes for people. You can do the same thing on the lunar surface. Yes, I'm coming from the mining industry. We're not very sophisticated. I'm sure you all have much more sophisticated solutions than this. But here we are. So that's it. That's what we do. We have to do the same thing. The overlap here, crossover, is automation. We have to replace all of the people in these mines with completely autonomous systems, and you have to do exactly the same thing to be successful on the moon. And that's the intersection between our 2 industries, making things fully autonomous at a distance. That's it. Thank you.
Thank you, Douglas. Other questions? Yes, there's one.
This is Will Coogan with Firefly Aerospace. You brought up a comparison between Apollo landers and current landers. We were one of the companies that landed on the moon. Is there not room for failure when you're, like in our case, all of our competitors are flying missions for less than 0.1% of the cost of the Apollo program? So is it okay, in your opinion, to have some failures in order to hit a lower price point, like per success?
We plan to have no failures. Failures happen. But you have to have a plan. And you have to have a backup plan, and a backup plan, and a backup plan. And that seems to be one of the things that's missing when we start to move down this track. We don't have to go there if it's fully autonomous. It's only if you actually involve individuals, you can't have a situation where you say, and even if it's volunteers, it doesn't matter that they're volunteers. The guys in our deep mines are all volunteers as well. They get paid to be down there. But that doesn't mean we can say, hey, if bad things happen, too bad for you. That is not the right answer. And so we have to change our thinking away from the fantasies that we've all grown up with. And these are really fantasies that we have.
Another quick question. Okay. Then I suggest... Yes, Advent.
Advent Maker from ESA. So you talk about abandoning the fantasy for the infrastructure. So according to you, what's the minimum infrastructure we need? What does it comprise?
The minimum infrastructure that we need is the infrastructure that we need to make sure, for example, if you've landed people on the moon, you need to have sufficient resources for them to live there until you can go back and get them. That's it. You have to have sufficient resources already put into our plant. If we build a mine in the most remote location, we have to have all the equipment, all the food that they need. If we plan that it will take us at least 3 months to get back there, we have to have 6 or 9 months material for them to live on. You can't just bank on the fact that, well, 2 people got stuck so they can hang out in the space station until we can conveniently go back and get them. That cannot be the answer. That can be the circumstance, but that can't be the plan.
Okay. Thanks, Douglas. So I think the contrast between the mining images that you showed and the microscopic images that we saw before is quite instructive about what challenges we are facing. We are going back to the minerals now. So the next talk is again on gamma spectroscopy. So it's Fabrizio Fiore from the Italian Institute for Astrophysics as well. And he's going to talk about PROGREX, a compact X-ray gamma ray spectrometer for prospecting of resources on planetary surfaces.
Thank you. I'm Fabrizio Fiore. I am an astrophysicist, but I also work on technology, in particular on technology of X-ray and gamma ray detectors. And I will give you a few more details on the project that Francesca presented before. So this is just to recall you that our targets are rare minerals on the surface of the moon. This is an old picture from Boeing. We are focusing on rare earths, platinum group metals, but also on iron and titanium on the moon. So these are our targets. So as Francesca was saying, we do have some evidence of rare earths on the moon, and these evidence are coming both from the Apollo and Chang'e sample return missions, but also from prospecting of the moon. For example, this is an image from Lunar Prospector, and also Kaguya did very nice images. The problem is that these evidences comes from very different scales. The footprint of the image that you are seeing here is 40 kilometers, while, of course, for the sample return, we are speaking about centimeters. So the main goal of our project, of the PROGREX project, is to bridge the gap between these two very large scales, from millimeters to tenths of kilometer scale. Because, of course, if you are looking at resources, you need to know where they are before organizing complex mining activities like the one that was presented before. So this is the CONOPS of our project. Francesca already showed this slide before. I just want to recall you the main idea. The main idea is that we are on a rover, and we use the rover in two ways. The first way is to make a scan, a 360 degrees scan, to understand in which direction there are excesses in the emission of the thorium, because as Francesca was saying, thorium is associated to rare earth elements. And this scan, so in this way we use gamma ray spectroscopy to understand which is the wide angle distribution of the thorium. Wide angle means scales of the order of 10 meters, 100 meters, or 1 kilometer. Then when we find a direction in which the thorium emission is high, we drive the rover toward that direction, and we use the other two instruments, Rescue, which is an hyperspectral visual camera that is assisted by LED that are emitting UV light to find UV fluorescent emission from rare earth, and Shy4D, that is a stereo camera with hyperspectral capabilities. This helps us to go from tens of meters, hundreds of meters scale to a scale of, let's say, 10 centimeters. And then we use XRF spectroscopy to really analyze the regolith and the samples down to a scale of millimeter or even less. So the instrument that I'm working on is basically the one that does both the gamma ray spectroscopy and the XRF spectroscopy. So this is based on an instrument that we developed for very different purposes. This instrument was developed to look at the sky to search for gamma ray bursts, which are huge cosmic explosions, so very different topic. This is an innovative instrument because it uses a technique that is called the C-switch, in which a silicon drift detector reads X-rays directly from the external, but also reads out optical photons produced by scintillation of gamma rays in a scintillation. We use a gag scintillation. This allows us to have a very broad band in a single instrument. This is a unique instrument. The very broad band goes from, let's say, 1 kV to a few MeV. So we cover with a single instrument both the X-ray part and the gamma ray part of the spectrum. And we have a decent energy resolution that is written over there. So this instrument has been developed by a very large consortium. A very interesting story is that the critical dedicated component, which is the sensors, the X-ray and optical sensors, the silicon drift detectors, and the front-end electronic, the ASICs, the optical filter, were all procured with research contracts, which brought down the cost factor of 10 times lower than commercial contracts. We use also commercial off-the-shelf component for the onboard computer, which was flight-proven, and electronic components, which were automotive. And we performed also radiation tests on these components to be sure that they were functioning in space. So these are the critical components I was telling you before. So these are the payloads that we produced, and the first one, FM1, was launched in the space at the end of the 2023 on board an Australian satellite, Spirit, and these are a few light curves and spectra obtained with this instrument. As you can see, we can in one single shot get data below 10 kV, but also above 100 kV. The emission line over there is the positron annihilation line that we used to calibrate the energy resolution of the instrument. So here the idea is to use the very same instrument to do the gamma ray wave field observations, and to use a smaller replica of the instrument associated with an X-ray source to perform XRF spectroscopy. So, as Francesca was saying, this project started in March, and it runs for 3 years. Basically, we are using, in our case, an heritage of an instrument that has TRL9, and we use also COTS component, flight-proven components. The other two instruments, Rescue, is based on COTS components which are flight proven, and therefore also this instrument is in a very advanced status of development. And the other instrument, Shy4D, is still use a heritage from a previous instrument, but it is in a slightly lower state of advancement. So we have emphasized in our project two main phases. The first one, at the end of this first year, we should be able to test breadboards to demonstrate our main technologies, but we have the goal of ending the project after 3 years, having in mind real demonstration models of these payloads to demonstrate the full functionality in the proper environment. So each demonstration model should be really representative of the main functionalities. And the important point is that we want that the demonstration model is conceived to be able to function on a rover, meaning that it should be compliant with all the interfaces. We are aiming at surviving only alpha lunar day, of course, and the minimum valuable product for us is functional and environmental tests on ground, using also mechanical anti-vac tests. But we also have the goal to perform functional tests in the proper lunar environment. Of course, if we are able to reach this goal, the added value will be to bring the TRL-29 for all the components, to test the planned operations, which are, as I showed you before, quite unique, and to test the observations of real lunar materials. I'll end with showing that this is a quite large collaboration involving several institutes in Italy, Europe, even China. And I'll stop here. Thank you for your attention.
Thank you very much. Are there questions? Okay, then I suggest, for the sake of time, we move on. Thanks again. So our next speaker is Christian Gscheidle from TU Munich, and he's going to talk about rover wheel-based permittivity sensors for prospecting of lunar water.
Yeah, so hello everyone. I'm here to present you some results from our feasibility study on rover wheel-based permittivity sensors for prospecting of lunar water. We did this at the Technical University of Munich under contract with ESA. Right. So quite similar to the previous talks, we're also trying to bridge that gap between orbital measurements and having a more local distribution, vertical distribution of water ice in our case. And what we're also interested is the density of the regolith. Right. And what we want to do is we want to use the regolith's thermoelectric properties, specifically the permittivity, electric permittivity. So the soil, which is basically a mixture of regolith, vacuum, and water ice, that acts as a dielectric between two poles of an electrode in an RC circuit, so from quite basic circuit. The nice part of that instrument is that we measure in situ, so we investigate the space right below the rover, and it's non-invasive, and so we can get can investigate pristine regolith. So a little bit of background on the electric permittivity of water ice. It kind of describes how much energy can be stored. So electric energy and charge can be stored inside a sample. And water ice, here in blue in the diagram, and also regolith, here in gray, have quite different static relative permittivities, and they also show different responses in the frequency domain. And so if we have a sample which has a certain porosity and then some ice included in it, that behaves differently when we measure it with our sensor. And so, as the regolith also is a quite good electric insulator, we can use simple geometries and simple configurations for the electrode. One caveat we have is that this measurement is quite temperature dependent, and so we also included temperature measurement capabilities in our instrument. Let me talk a bit about the heritage for our sensors. So especially the electronics concept is strongly based on the ESA Prospect sensor, which Dave Heather also already talked yesterday about. And here you can see our prototype of the permittivity sensor in a close-up. Just the electrode, not the electronics. The electronics is located inside the drill, and that's a difference, quite a big one actually, compared to our rover permittivity sensor. We had some other activities on permittivity sensors going on at TUM, specifically here on the right side, some patch electrodes which we tested with lunar regolith and icy lunar regolith, and also some other missions were able to show that these measurements are quite powerful, including the Hazy PVR on Cassini-Huygens and the Sesame PP on Rosetta Philae, which was one of the few instruments which was able to actually return some data, and also for the HB Cube mission or instrument on InSight, there was a concept which unfortunately was not implemented. So I talked a lot about the background. How does our sensor actually look like? This whole project is centered around the Rashid rover from the Mohammed bin Rashid Space Center of the United Arab Emirates. And our ESA project is then in collaboration or in cooperation with this rover. Here on the top you see the Rashid rover 1 design, or Rashid 1 rover design. We are planning to include our sensor onto the wheels of the Rashid 3 rover, so that will probably look somewhat different. We will include 2, maybe 3 electrodes on the rover wheel. You can see that in that rendering here. And so we get the measurement depth is dependent on the size of the electrodes, and so we can measure different depth. How do we operate the sensor? So as the rover drives along the lunar surface, every time an electrode is in contact or in very close vicinity of the regolith, we get a data point, and one of the measurements they take depending on the fidelity of the measurement, around a minute. We also include the temperature sensor. You can see a little nupsy on the bottom electrode. That's a resistive PD1000 thermometer, and we also included our infrared temperature measurement sensor. That will be rover body mounted. So these are pictures from our prototypes. We implemented all these electronics on our backend electronics board, which is then supposed to go inside the rover. We expanded the functionality compared to the Prospect electrode, so we have a more capable sensor and a more flexible one. The infrared temperature sensor is then directly connected to that electronics. And one big issue with the electrodes being located on the wheel and the electronics being inside the rover is that we have to kind of bridge that connection in the axle of the rover wheels. And so we are developing a pancake slip ring, which can vary the signal. That's a coaxial slip ring, so that the measurement is quite susceptible to noise. And so we have a coaxial pancake slip ring also as part of our development. We have end-to-end tested this prototype. Here you can see this quite small, quite light, so that's our instrument doesn't require a lot of power or a lot of mass, some volume for the slip ring, and obviously we need some real estate on the rover wheels. Yeah, but with this, we were able to actually show this added capability of frequency shifting. So when we just switch on our instrument, we start at a certain frequency, and then that shifts, and so has different resolutions in the frequency space. Also, we were able to verify the measurement principle. You can see that characteristic peak depending on how much capacitance we attach, or how much regolith there is beneath the electrodes and the wheels. We were also able to show the capabilities of the temperature sensor. We evaluated different thermopile sensors and configurations in our cryogenic vacuum chamber down to around the minus 150 degrees Celsius target temperature. So that should be quite representative. And for all investigated sensors and combinations, we got a fairly linear response over the entire temperature domain, and thus we were also able to show the feasibility of this part of our instrument. Right. So we think that electric permittivity sensors are a promising concept for planetary surface exploration. We can map the water content and also the composition of the subsurface regolith along the rover traverse, and so we get like a data point with every revolution, or rather two if we have more electrodes, and so get a lot better resolution than orbital measurements. Our sensor is quite robust, and we can integrate it onto various systems, not only rover wheels, but also, as you see, with prospect into drills or penetrators or lander footpaths. And in general, the instrument does not require a lot of data, or it generates data, but that can be handled quite nicely. We don't need a lot of power, and it's also quite light, so the entire instrument is around 0.5 kilo. Mind you that we have that big slip ring, which takes quite a bit of our power budget, mass budget. And for the flight with the Rashid 3, our ESA contract, so for the following phase, will kick off in Q2 of this year. And we will build a proper engineering model and a flight model for this. And we expect Rashid 3 to launch with RPS in 2028. And with this, I'm ready, and I'm happy to take any questions.
Thanks a lot. So, other questions?
Yeah.
Yes. Marco.
Hi, Marco from ESRIC. You mentioned the depth of the detection. Also, I have some parameters that it depends on the electrodes. Could you please tell us about what is the penetration depth that you can get? And the second question that would be connected to that would be, what is the depth that maybe it's good to look up to? What would be interesting to us to, how deep should it go to be also interesting? What's the limit as well? Thanks.
So thank you for the questions. For the first part, the size of the electrodes kind of limits how deep we can go, and that's fairly in the same order of magnitude. So with the current instrument, we're around 10 centimeters. We can investigate the top 10 centimeters. And if we increase the size of the electrodes, we can go deeper. But that there is no inherent limit to that. Maybe if we have electrodes on different wheels, we can investigate all the sample below the rover, but I can't give you a number for that value. Hope that answers it. Other questions?
Any other questions? I've got one. So in one of your figures, you showed that the response of iron and titanium oxides, it's quite similar to water. So is that true? And could you use it to map out, for example, ilmenite concentrations?
Mm-hmm. That was the static permittivity, and so we used like a spectrum in the frequency domain to distinguish water. and titanium doesn't have that. So it might be possible. That's maybe something to look into in the future, into mineral composition, but we have not investigated this yet.
Thank you. Thank you. So we move on. The next speaker is Daniel Angerhausen from ETH Zürich, and he's going to present about variational autoencoders for discovery of anomalous features in ultra-large lunar and planetary data.
Yes, hi everyone, I'm Daniel, as we heard already, senior scientist at ETH in Zurich, also at the SETI Institute partly, and I'm by training an astrophysicist and astrobiologist, so I'm quite a newbie in this community here, so I thought I'd tell you a bit the story, how we went from searching for aliens to maybe starting a venture in lunar prospecting, so bear with me here. And there might actually be aliens in the end, if you pay attention and stay with me to the end. So my entry to the field of lunar data and also machine learning was about 6 years ago. That was also where I met my two collaborators, Adam and Valentin, at the NASA Frontier Development Lab at the SETI Institute at that time, at NASA Ames. I know there's a bunch of alumni in the audience here. I think there were also a couple of projects from FDL presented here in the last years. So just for those not so familiar with it, this is essentially an 8-week incubator sprint in summer. It's a collaboration of various Silicon Valley partners who essentially give free compute to the group of machine learning experts, but also machine learning experts and domain experts who just work for 8 weeks on very challenging problems in space science defined by NASA and other experts. So that's in a nutshell what we do, what we did at FDL. One project that I just want to mention how it started for us was this, in quotation marks, metal detector that we developed in the 2019 team. And that challenge was actually partners with LSA, if I'm not mistaken. So in a sense, this disruptive investment of LSA 6 years ago brought me over a couple of ripples again here. So you see this stuff, has third and fourth order, follow-up ideas maybe. So long story short, we worked on this 8-week super intense, challenging program at the SETI Institute. You run into Frank Drake once in a while. You meet other big SETI scientists. So you sometimes get crazy ideas. And our basic idea was, and we literally sat in a Starbucks in Mountain View, so in the heart of the Silicon Valley, and had this idea. So what if we train a machine learning model to find the Apollo landing sites? Completely agnostically, unsupervised learning. First of all, would it be able to find the Apollo landing sites? And then if it finds the Apollo landing sites, what else does it find? And this was really coming from this, idea of SETI and technosignatures. Maybe we find an obelisk on the moon or crashed UFOs or, secret bases of prehistoric civilizations and whatnot. So it was really this kind of crazy SETI idea. And this was also not a new idea. So, for example, Paul Davis, a really distinguished professor from Arizona, had this idea in this paper about 2013, so searching for alien artifacts on the moon. And he writes there, it might be possible to scan the entire data set by crowdsourcing the work to a few tens of thousands of people over the internet. And then they actually employed a small pool of students and faculty to search the NAC images for interesting features. So these poor grad students were probably swiping through lunar images for weeks and days to find anomalies in the data set. And then, of course, we thought, yeah, that sounds a lot like a machine learning problem to us. So this is how we started to it. Briefly, we use so-called autoencoder architecture. So it's really, in a nutshell, this structure you can see here. So it's this hourglass-shaped network where you put all your images in on one side, and then you reduce the dimension to this bottleneck, and then you have this decoder part who reproduces the image again, and then you do it again and again and again until what you put in the beginning looks like what you get out in the end. And then you have learned essentially this low-dimensional representation of the whole data set in this latent space. And then you can do all sorts of crazy things. You can use the decoder as a generative model to fake lunar images. You can use this latent space as a compressed, essentially a compression of this data set. And what we use this autoencoder for, so I love autoencoders, they are super versatile. So what we used it for was for this agnostic search for anomalies. And we did this by what we call looking at the reconstruction loss. So essentially we looked at how good can our model actually reproduce the image we put in the beginning. And if it's just run-of-the-mill, typical image of the moon, as you can see here, it's very nicely reproduced, so you have a very low reconstruction loss. But then if you put in something more crazy that is out of the distribution, it becomes harder and harder for this network to really reproduce this image. And this is what we call reconstruction loss, so the ability of this model that learned the whole data set to reproduce individual images. And this essentially became our anomaly score. And this is what we then run for a bunch of patches of the lunar surface. So you can see here, we took this, I think, 50,000 times 30,000 batches of LROC data, cut it in this 64 times 64 images. Then we fed it through our autoencoder, or first of all trained the autoencoder and then did inference on all of these images. And then you see in the center, we got this distribution of anomaly scores. So you get this big peak of really low anomaly scores. This is essentially your, standard, boring, typical, lunar surface with craters and whatnot. And then in this tail of the distribution, you see all these anomalies. So for example, here you see these orange arrows are the Apollo 15 landers. And then it turned out we not only find these techno-signatures, so these human signatures of technology on the moon, but also all sorts of other interesting things. So in this case, for example, outcrops or rockfalls. So this was a surprise to us in a sense. So we were looking for aliens and then find all these other potentially for you folks and for lunar prospecting interesting things like volcanic pits, entrances to caves where you want to build your lunar hotel, these irregular mare patches which might be hotspots for certain types of resources you want to harvest, recent impacts which might have just delivered something interesting to you, these rock falls that tell us a lot about the seismic history of the moon. So that was kind of cool for us, right? So we find all these other things, not just the aliens and not just the Apollo landing sites. So we got all these anomalies. So then we published this, I think about a year ago, and thought, yeah, cool, now we can take this, scan the full lunar surface. So right now we only work patches of it. It's about 2-3% of the lunar surface. So we thought, this is a nice science project. We can go on. We can also go for other scales, look for, smaller anomalies, larger anomalies, also maybe expand it to high-rise data from Mars or, other data sets from the solar system that might be interesting in terms of, anomalies that might be, useful in whatever context. So we applied for science money. So we went to our NCCR, so our National Competence Center for Research in Switzerland, and thought, yeah, this is a cool science question, and I still believe that. And they were like, review or 2 or 3 were like, yeah, it's maybe not such a cool science question, but what about commercialization? And we're like, sure, we can also look into commercial applications. So instead of money for science, we got a bit of seed funding to look if there might be some sort of commercial applications of these algorithms, so not just the anomaly detector, also other machine learning methods we developed for lunar data. And then we got into a program called Bench to Biz, so a bit of this laboratory to market program, a bit of a startup training that we got as so-called idea champions. And then really got into this idea of maybe we can use this stuff for lunar prospecting. And I want to close, and this is why I'm here, talk to you if you have data sets that you think might be interesting for it, if some of these anomalies I showed are interested for your science cases, start talking to me. And I want to finish up with one of my favorite anomalies. So I leave that up to you what we see here. So this is the same place on the moon from different illumination angles or different illumination angles. I'm not saying it's aliens. If someone from the History Channel is here, I might say on camera, we will see. So so come see me in the coffee break if that's interesting to you. And if you want to know where that is, bring cash and I tell you. Thank you.
Thank you. Other questions? Anyone asking what this is? Yes, Pavel.
Okay, thank you. Very interesting concept. I was considering also working with convolution neural networks. Would you be able to improve your model for finding some patterns in the images to really fine-tune it in terms of like getting rid of some anomalies that you find, that you just filter them out, you don't even need to look on them?
Yeah, great question. So right now it's a completely agnostic search. So it's really, we feed the images in and we just get this tail of the distribution which is anomalous, and there's all sorts of different, unsupervised whatever anomalies. And now we're actually thinking about the next step. So take this, 2 orders of magnitude smaller set, which is in the tail of the distribution, and then do some sort of semi-supervised or supervised learning to, cluster the rock faults here and find the outcrops there and make sure we get rid of all the get sure of all the instrument maybe dead pixels or whatever could be an anomaly too. So yeah, this is the next step, to really combine this so far very agnostic unsupervised method with some sort of more maybe domain knowledge, including physical solutions. Yeah.
And Inna.
Yes. Follow-up question: what are the limitations?
For us, at the moment, it's compute. So it's, as all of this, and this is, I'm not sure if I mentioned this, so this was really, it's not my main science, so this is really more like a hobby is maybe said too much, but it was really a side project of a side project, and right now the main problem for us was to get compute. So this is compute. It's terabytes of LROC data that you have to feed through a machine learning algorithm. The PDS, honestly, is also not made for this. So the PDS is made for, some scientists downloading one image, look at it, and so it's not made for batches, of gigabytes that you funnel through machine learning. So I think this is the main bottlenecks right now. It's like compute on one hand, and then also I think the databases are not just made for machine learning applications right now. So we should look at some sort of mirrors that are built for machine learning. Yeah.
Great. There's one quick question in the back.
Thanks for the nice talk. It might be a stupid question, but if 2 meteors coming towards the surface, they make 2 long trails on the surface like this. And if a rover going with its 4 tires make the same shape, does it differentiate between the 2 or?
Yeah, this is a bit what we just talked about, right? So right now it's super agnostic. It just says, okay, this is weird to me, right? And it could be a rockfall, it could be an outcrop, it could be a mirror patch. But then the next step indeed is to, see if we find some more, semi-supervised or supervised method that can actually distinguish. But that then probably means that you need, again, a bunch of people, manually label it. You need really domain knowledge. Like, first of all, I think you need a human that is able to distinguish, like a rockfall from a tracker. This might already be hard enough. So I think bottom line is if a human can distinguish it, probably also the machine can. But if you can't distinguish a robot track from rockfall, then it might also not be possible with machine learning. Yeah.
And are you testing that with the telescopic data that we obtain here with telescopes?
I mean, this is data from lunar reconnaissance orbiter, right? So it's a telescope, a space telescope orbiting the moon, looking down. So, yeah.
Okay, thanks again. So we move on to the last talk of the session, and this is Uwarowa from Lightigo, and she's going to talk about laser-induced breakdown spectroscopy as a prospecting technology for commercial ISRU missions.
Thank you very much. Last presentation, I'll try to keep it short, but having advantage to have last presentation means that I will highlight several topics which were already presented, and especially very happy to hear that LEAPS was considered as one of the methods. We truly believe in this methodology because the mother company of Lightigo Space is a spin-off from the university where there is a very strong group on LEAPS. So we have a lot of expertise, and we are now incubated in ESRIC to bring basically our expertise and LIPS methodology for space in situ research prospecting, not only on the moon, because as you know, this method was already flying on the Mars missions. The moon is just, by the time frame, is a bit more closer. So what we are prospecting on the moon, I will not repeat, because I heard many people talking about what is interesting. I just want to conclude what we've learned during the couple of months of researching. So the scientific interest and the commercial interest, they're a little bit different. The scientists are looking for very specific things, especially isotopes, because they want to understand where this hydrogen is coming from, where are the history of the moon, and so on. And for the commercial, of course, we still would like to speak a bit more with commercial teams, with the commercial rovers, and I invite to talk to us, to collaborate, for us to better understand what are the requirements, but we clearly see that it's a little bit different. And basically the conclusion is that the requirements for the performance of the instrument might be a bit different, whether it is for scientific or commercial ISRU mission. For those of you who don't know what is LIPS technology, I want to briefly explain. So basically it works the way that you can be in a certain distance from the sample. You don't need to prepare it, you don't need to touch it. It's really dependent on the pressure. As on the moon for LIPS, the conditions are quite challenging. So we have to be a bit closer than we are normally, let's say, on terrestrial application, where we can go in terrestrial up to 20 meters. On the moon, we have to be around 10 centimeters, in the centimeters to 15 centimeters above the sample, which means that we can be basically on the rover. And the method works the way that you shoot the laser, you ablate the surface, and then you do spectroscopy from this ablation, and then the result is basically the spectra, and you can detect the elements. As I said, the technology is maybe not super new, although majority of the missions were on Mars rovers. What is interesting is also that if you see the missions, there is the NASA 2 missions, a Chinese mission, and the Indian. But for example, European mission never had the LIPS instrument, although the European team were supporting NASA and Chinese mission for development. But in Europe, we never had so far launched any mission. Also, Japan, they are preparing, but they never used it on their mission. But I see that it's more and more interesting for the science team to use this technology. As I said, from the results, these are the results from the previous missions. On the right-hand side, you can see the Mars mission, and on the left, Indian moon. So the main difference for this methodology, as I said, is very dependent on the pressure condition because of how plasma is expanding. So when we have a low pressure, the plasma is expanding extremely fast. So the quality and intensity of the signal is much lower. So it's a bit more challenging and difficult to get the spectra. There is a lot of noise. So the signal to noise ratio is much worse than, for example, on the Mars, where we have some pressure. Here you see basically what I said, that how the plasma is expanding. So for us, Mars is, let's say, technologically is less challenging. Moon is a bit more, but Moon brings also another opportunity. And this another opportunity is basically because, as I explained, how the LIPS works, that you have like initiation and then you sensing. So if you change the way you sensing, for example, putting the mass spec, then you can, because normally for the mass spectrometer type of orbit trap, you need to accelerate the particles. Here, as plasma is expanding very fast, they are already at the speed which is enough to bring them to the orbit trap to detect. And although this sensing is much more advanced than normal spectroscopy, but it gives a very precise result and the detection of the isotopes. So if, like from the science point of view, if it's needed to really track very detailed data, then it's also a way, an opportunity. And there have been some missions already either planned, either flying the instruments to combine basically mass spectrometry with laser induction. So here you see the data product, basically the spectra. This methodology is very good for the light elements and also as we are developing basically the instrument as a company, it's also a big advantage because there are not many companies, there are not many types of these instruments available commercially. We try to optimize the instrument also in terms of the cost and the time for delivery. And it means that partially we develop some of the parts of the system ourselves. It means that we can also fine-tune it to the needs and, for example, fine-tune it to the range that is important for detection. So depending on which are your requirements to which elements you want to detect, the spectral range can be narrowed, so we have better results, we have better intensity. When we make the spectral range wider, of course, the intensity is dropping, but there are like several options how to resolve it by adding several spectrometers or like choosing exactly the range. So the performance of the space version, as I said, we are trying to miniaturize it, and the prototype is under development, and the laser is commercial. We will be qualifying it. It's a terrestrial laser. Unfortunately, there is not many lasers available like from the shelf space grade for these applications. But spectrometer can be developed inside the company. We have a competence, also the optics and the electronics to control it. So the like overall dimensions, they are mainly driven by the performance requirements. So basically, for now, the instrument is around 20 to 80 millimeters. Around 3 to 4 kilograms, and the power consumption, I think, is a few watts, because the measurements are also not that fast as, for example, in terrestrial application, where we can do even the mapping of the, yes, and this is our vision, how we would like to implement it. We also have the demonstration just after this presentation, where this instrument is not only on the rover for prospection, but it can be implemented in the process, in the cycle of utilization of the resources. I have to move on. But basically, as I said, you don't need any preparation, you just can implement it on the chassis of the rover and perform the analysis. Yes, so also when, for example, there are the plans to recycle the regolith or to build something from the regolith to 3D print and so on, in this step, it's also very important, or when we do the purification of the water, it is possible also to check the quality with this instrument. So we targeting TRL-9 ready to be flown, let's say in 28, 29. Looking for a mission with which we will go. So I invite also you to collaborate, and just a short showcase on the terrestrial application. So basically for mining, you can see that the method is very fast, and it allows also basically to scan and detect the minerals. And the last thing is we are also developing the special chamber where we can implement different atmospheric conditions to test samples in the conditions of Mars, Moon, and so on. Thank you very much.
Thank you, Inna. Other questions? Yes, I see several hands. There's one in the aisle.
Okay. Do you have any early laboratory results? Do you have any early laboratory results on the sensitivity/detection limit for light elements, so hydrogen and oxygen, for instance, under simulated lunar conditions? Thinking of the effect of the pressure?
Yes, we have some preliminary. The one that I showed, they are very preliminary, but now we are also conducting the testing in these weeks, these days. I just got the message with the new results. So it's happening. If you're interested, please come. We have also here my colleague, Pavel, who is a professor at the group for researching the LIBS in space.
Gotcha, thanks.
Lucas?
Jakub Ciążela, Mirror-S. My question is, what is your detection limit for sulfur on the moon?
I think it's hundreds of ppm.
Thank you.
Okay, are there more questions? Otherwise, this concludes the session and we're perfectly on time. There's one, just to go a little bit over.
Well, it's relatively technical. We can talk later, but I wanted to ask, first of all, do you use a standard 1064 nanometer laser for the LIBS, and if you tried some other wavelength, and specifically for the moon, can you comment regarding the accuracy of let's say, alteration of a sample with laser ablation?
Yes, we did actually the trade-off of the types of the laser and also the wavelength. Initially, we went with what is most popular and what the other missions used. But there is also the trade-off that I can share to check why this wavelength.
Excellent. Any other questions? Okay. Then I suggest we go into the coffee break. Thank you for being here. Thanks to all the speakers again, and thanks to the team in the back.